All right, now let me tell you a version of Ramsey's theorem in terms of infinite graphs or the infinite sets. All right, so here's a theorem. Again, this is called the infinite Ramsey. Okay, let me state this way. So in any C coloring of all two subsets of n, okay, let me say n is 1, 2, 3. In any C coloring of all two subsets of n, there exists an infinite subset X whose all two subsets have the same color. So no matter how I color the subsets of size 2 in one of these constant many colors, right, I can find this infinite subset where all the subsets of size 2 have the same color. Or in other words, any CH coloring of K omega. So K omega is a graph on infinite graph on n, infinite complete graph on n, has a monochromatic copy of K omega. Of course, you can, this 2 is not really needed. You can replace this 2 by any number m. It doesn't matter. But for simplicity, I'm going to show you this version. Right. Now, what we do is, let's S1 be this number, the set of all numbers. And I'm going to recursively build Si. Suppose Si is given, so we're going to build the Si plus 1, right? Now, let's pick some vertex in Xi. All right. Okay, let me more precisely. Xi and x1, x2, xi are given I minus 1. Given, choose xi in Si. Oh, by the way, Si is a subset of n, and Si is infinite. Now, since Si is infinite, I can find an Xi which is not equal to x1 up to Xi minus 1. And then look at all sets of size 2 containing Xi. Choose a color, let's say CJ, such that there are infinitely many 2 subsets of color CJ, no, not CJ, CI, containing Xi, right? Because you have an infinite, containing Xi and another element of Si. So here's x1, x2, xi. Now I look at all sets of size 2 containing xi, and then look at all the colors. Among all the colors, I choose the one that appears infinitely many. That's the color Ci. Then I'm going to restrict Si plus 1 be the union of this together with all y such that y is in Si and Xi and has color J, color not J, X, color CJ, CI. So that's how I build the Si plus 1. So repeat this. Then we have a sequence x1, x2, right? This is infinite sequence. So among all Ci's, there is one choice. I cannot use C, so that one choice K that appears infinitely many times. And then let's say Ci1, Ci2, Ci3, all these things are K, where I1, I2, I3. Then take X to be Xi1, Xi2, Xi3. Okay, now what's going to happen? Now consider all sets of size 2. This has color K because the color depends on CIA, but this CIA is equal to K, right? So that's the infinite Ramsey. So I have an infinite monochromatic subgraph. All right. Now, interestingly, this actually implies the finite version without explicit bound. That's what we call the compactness principle. And in many cases, in many Ramsey type theorems, if you have an infinite version, then you also have a finite version. All right. So that's the. Let me tell you the reason. So let me talk about the hypergraphs. H is hypergraph if H is equal to VE, where V is a set and E is a set of subsets. Okay, then we call it a hypergraph. So graph is hypergraph. I mean, simple graph is a hypergraph because each edge is associated with two subsets, subsets of size 2. Now I can talk about the chromatic number. Chromatic number is a minimum C such that there exists a function f from V of H, the vertices of H, to one of the C, right? With the property that no edge of H is monochromatic. No edge has only one color. Now, why is this chromatic number problem related to Ramsey problem? So this is called the chromatic number. And the thing is, let's think of this example. So Ramsey number RK, RKK. Right, so we are coloring the edges of the graph so that, right? So they consider a hypergraph H on where V over H is the edges of G, edges of Kn, and E over H are the case edges of a copy of Kk in Kn, right? Then what does that mean? That means then let's look at the chromatic number. If the chromatic number is bigger than C, that means no matter how I color by C colors, okay, 2, let's say 2, no matter how I color by 2 colors, I can find the monochromatic edge. But monochromatic edge means that I can find the copy of Kk, which is monochromatic. So this means that Ramsey number of Kk is bigger than n, right? So these two things are related. I mean, in certain constructions, right? So if you can show that a hypergraph has high chromatic number, then Ramsey number is big. Or the other way around, right? If Ramsey number is smaller than something, then chromatic number is smaller than something, right? It's a contrapositive statement. Now, with this observation, now we're gonna show you this compactness principle. Let H be a hypergraph such that all edges are finite. All edges are finite, and we don't assume that V is finite. Let R be a constant. If the chromatic number of H induced on W is at most R for any finite set W, then the chromatic number H is at most R. This is what's called the compactness of the chromatic number of a hypergraph. Right? Now, more convenient form for us is the following. If chromatic number of all induced subgraph is bigger than R, then the chromatic number of a whole graph is bigger than R. Oh, no, the other way around. Anyway, yes, right. So for us, more convenient form is if this number is bigger than R, then there exists a finite subgraph H prime such that chi of H prime is bigger than R. Okay. Anyway, I'm going to show you the two proofs. The first proof assumes that V is countably infinite. So suppose V is 1, 2, 3. I mean, I could just say n. We can assume this, right? So for all positive integers n, there is a coloring fn from n to 1 up to r. No, not n. 1 up to n to 1 up to r such that no edge of h induced on 1 up to n is monochromatic. Right, that's the definition. I mean, that's the assumption, right? For any finite subgraph, you have a coloring. Now we're going to define coloring as follows. So suppose f1, f2, fj minus 1 are already defined. So that sj minus 1, which is the set of n integers n which is bigger than j minus 1, and fi equals fi and I for all 1 up to j minus 1 is infinite. Right. All right. Now, right. I mean, the idea is that we'd want to choose f of j such that the number of n with f of ni is equal to f of I for all I from 1 up to j is infinite. Right? Because there are only finitely many possible values, by Pigeonhole principle, there is a choice fj such that this is possible. Right? So that's how we define fj. So in other words, so in the beginning we choose f1 so that there are infinitely many n such that fn1 is equal to f1. And then we choose f2 so that there are infinitely many n such that f1 is equal to fn1, f2 is equal to fn2, and then we choose f3, etc. Right? So this is how we choose this thing. So the property is that for any I, there are infinitely many n such that n is bigger than I, and fn1 is f1, fn2 is f2, fn I is fi. Right? Now, we need to show that why this is a good coloring. A proper R coloring. Why? Well, if there is a monochromatic edge in H, then since each edge is finite, there is n such that, okay, let's say this edge is in there is I such that the edge is included in the subset 1 from I, then okay, let's say n. Okay, maybe n. Okay, I is better. I. Then there is n bigger than I such that fn1 is f1, fn2 is f2, fni is fi. So in Fn, X is a monochromatic edge of H1 up to I, 1 up to N. That's contradiction because Fn is chosen to be the coloring such that no edge is monochromatic. All right, so that's the first proof. This proof only works when the set of vertices is countable. Now, if you have taken the topology course, I can show you the second proof. Second proof works for a general case, but it assumes the axiom of choice. So what we do is we consider the set T of all functions, set of all functions f from V to 1 up to R. All right, now think of it, you can think of as follows, right? So the 1 up to R, right? For each vertex, I'm taking product of this finite set, 1 up to R, and we give a discrete topology to 1 up to R, so that any subset of this is open and closed. Now, then for this product, we have a product topology. So meaning that we have a basis, right? So product of something is a basis if xv is equal to 1 up to R for all but finitely many v. And then anything you can obtain by having a union of them will be open. Right? And then we use the Tikhonov theorem by the Tikhonov theorem. Yeah, I think I made a typo here. This thing T is compact. Because 1 up to R is compact. Right? So the product of the compact set is a compact. So for a finite set, W, a finite subset of for a finite subset W of V, let Fw be the set of functions f in T such that no subset of W is a monochromatic edge in F, right? So if you think of F as a coloring, then in W, no edge is monochromatic. Then Fw is closed. Why? Because its complement is 1. You pick an edge inside W and then consider all possible functions where this is monochromatic, and that's open set. And then you're taking union of finitely many open set, which is open. A union of, oh no, not the union, okay, right, that's 1. Yeah, it is union of finitely many open sets. That's right. So for each edge, you look at all possible coloring with that edge monochromatic, and take a union of all these things, and then complement of that. So that's closed. All right. And since there are only finitely many colors, this is defined. Now we use the assumption, since chi of HW is at most R. What does that mean? That means Fw is non-empty, right? There is at least one coloring where no edge is monochromatic. Now, if W1, W2, Wt are finite subsets of V, then what is let's look at their intersection. Right? Their intersection, well, so it's a set of colorings where no monochromatic edge inside W1, no monochromatic edge inside W2, etc. Well, that certainly contains a set of colorings where no monochromatic edges inside the union of Wi's, but this is non-empty. So Fw, so collection of all so this has the property that every finite intersection is non-empty. All right, and T is compact. That means intersection of all W is non-empty. So let F be in the intersection of all W, then no edge is monochromatic. In F. Okay, so that's the proof using compactness and axiom of choice, because the Tikhonov theorem requires axiom of choice. And indeed, actually, you need the axiom of choice to prove this theorem. So why did I talk about this theorem? I'm gonna show you as a corollary of the infinite Ramsey. Right, so let's go back. So if you have an infinite version, we can actually prove the finite version. Right, so here's we have infinite version, right? So whenever you color all two subsets of natural numbers, then there is a infinite subset where all two subsets have same color. Now what we're gonna do is for all t and c, there exists n0 such that if n is bigger than n0 and or subsets, all two subsets of 1 up to n are colored by C colors, then there exists a T subset of 1 up to n whose all two subsets have the same color. Right, this is the usual Ramsey theorem, right? So Ramsey of T. Now, so we already know how to prove it, but now I'm going to show you how to prove it by using the infinite Ramsey and by using compactness. So let H be a hypergraph whose vertices are the two subsets of n and edges are the T subsets. Okay, edges are two subsets of T subsets. Right? So each edge becomes a vertex, and set of okay, I didn't use the graph, right? So each subset of size 2 become a vertex of hypergraph, and whenever I have a set of size t, then all subsets of size 2, collection of all subsets of size 2 inside this set is becoming an edge of this hypergraph. By the infinite Ramsey, any C coloring of H, any C coloring of N, any C coloring of two subsets of N has an infinite set, monochromatic subset. This implies that chromatic number of this H is bigger than C. Right. So by the compactness, there is a finite set W such that chromatic number of H induced on W is big. But this W could be arbitrary set of subsets of size 2, so we may assume that W is the set of two subsets of a set X, which is a subset of some n0. Okay, set of all two subsets. Because adding more edges doesn't decrease the chromatic number. This means that, so since chromatic number HW is bigger than C, so any C coloring of two subsets of 1 up to n0 creates a subset of size T that is monochromatic. Okay, so that's the proof. Now, let me go back here. So the thing is, so we construct this hypergraph by infinite Ramsey. Any C coloring must create a monochromatic subset, infinite subset. Inside the infinite subset, you must have a T subset of T subset, and that's why these edges are monochromatic. So chromatic number has to be bigger than C. All right. So this infinite version implies the finite version of the Ramsey's theorem. And this is true for many other variants, which we are going to cover. So whenever we have an infinite version, we also have a corresponding finite version.